Mic's on, you can hear me back there? All right, so I'm Chad Gibbons, I'm a Director of Engineering at AlertLogic, and I'm gonna tell you a story. And it's a story about our journey to using microservices in Erlang, how we got there, and how it worked out for us. I talk about the buzzwords in the title of the talk because we really touch upon every single one of these instances of buzzwordy stuff when we created our system, really out of necessity. Let me give you some context about who we are and why we got here. There's a little bit of history involved here, but it makes a lot of sense. So AlertLogic as a company, we're a security as a service company. And really what we do is we monitor our customers' networks. We're ingesting so much data from these customers, and we figure out if there's a security vulnerability or if there's an active security attack, and then we notify them, right? So it's kind of the enterprise monitoring problem, but focused on security. Part of that is actually we have also a security operations center filled with hackers that actually knows how to hack things and what hackers would do, and we use that as an expertise bridge to our customers. When we talk about data, I love this graph. I made this the other day. This is actually real. So right now we ingest 1.6 petabytes of data per month, and we're planning for 100 petabytes per month in just a few years. And our growth rate has been like that since the inception of the company, sometimes bigger, sometimes slower, but generally it comes like this. This is not only from adding new customers, we're at 4,000 today. This is from the customers adding more data, as you would expect, and for us adding more data sources. So you can imagine the problem space that we're in is truly big, and there's a lot to worry about and a lot of distributed systems to manage that. So our engineering history, and this is really important to figure out how we got on this path that we were on. The company's been around since 2002, and early on it was really about taking open source tools and making them work for a service. And that's really what was built. There was a lot of Perl code, and all the integration between these pieces of code was done at the database layer. We had a lot of MySQL-based integration, and years later was proven to be very problematic. That changed pretty significantly around 2005. They got a bunch of funding. The company grew quite a bit. We hired some world-class engineers. This is when we started using Erlang. What came out of that period was a new product within the company to ingest customers' log files, which you can imagine is a lot of data, because we ingest all of them. What we built out of that was a cluster, a grid cluster, and it's almost like a real-time version of Hadoop if you want to think about it. That's our big Erlang infrastructure that we still use today. Very powerful for a certain kind of computing model. A few years later, and this is about the time that I started at the company in 2011, we grew again, had a bunch of new engineers, new ideas, new products. That model of computing with Erlang didn't really apply to what was being built at that time. So we kind of went off on our own and did different things, and there were different implementations of Erlang modules. We had like 2 or 3 versions of Erlang logging and 2 and 3 versions of Erlang web servers, and it was kind of a mess. And when I came in my role, and I was an architect at the time, one thing I would point out is that we didn't really have a company culture in engineering. And it was real apparent. It was just little silos, even within engineering. So about that time, so 2013, we wanted a new approach, not only from the business, but also from engineering. The business really wanted to make another big leap in technology, but we couldn't really do it on the foundation we had built before. So I did a proposal, and we were like, let's make a new platform from scratch. Let's go off, do a skunkworks project, figure out how to do something new, see how we can apply it to our current business and a future business. And we really wanted to define an engineering culture out of that. So like 6 or 7 of us went off, and we did exactly that. I had the chief architect role at that time, and I had 6 peers plus a business guy that were all about the same level. So we had a lot of chiefs in the room, a lot of discussions about what we should do, a lot of disagreement, but we came down to a set of principles. And I'll talk you through all those principles, and that really is the heart of what we did here. The first was we really wanted to decide what we were going to build on. We could build a cluster computing system again, or we could do web services or something completely different, and we decided distributed microservices made a lot of sense. I had been doing those in most of my career in one way or the other, and seen them work in a production context, especially for software as a service. We really wanted to focus on the software interfaces, not database interfaces or anything like that. So we just said from the get-go, everything's going to be either a REST API or publish subscribe messaging, and we'll deal with that As it was before then, there wasn't a standard within the company about how components should talk to each other. We also wanted to recognize Conway's law, and if you're not familiar with this one, this is the one that basically says software architecture and organizational structures match. And if they don't match, they will eventually, whether you want to or not. So you might as well recognize and embrace that. And what that really meant for us was let the teams really own components and focus on them, not have components shared across teams or anything like that, because that winds up not working that well. This one was my favorite, as chief architect. This one is the one we debated the most. Mandate as little as possible. Some of us wanted to mandate everything, like thou shalt use Erlang. You should do it this way. And it was a lot of back and forth. And we kind of came down to how would we want to be treated if an architecture team came to us and said, do it this way. So we really wanted to focus on the interfaces, not the particular implementations. Document the standards of how things should talk. What's funny about this one is years later, the one guy that was the most adamant about us being open was the one that wanted to make things more strict as the company grew. So people can change their mind over time. So we came up with a set of design principles. I'll go through them now, and a set of best practices. And it's really interesting to even say, use best practices. And yet, I think all of you have probably had the experience where the industry best practice is known and engineers go off and do something different. We kind of wanted to change that. All right, so let's go through the design principles, and this is really what we decided to do from the get-go. First one is everything is an API. There's no exception to that. It doesn't matter if you're making a microservice that's designed to be an API or something that just processes data, everything has an API. We use that not only for the software interface itself, but also for our monitoring and our control. Like a simple example of that would be a health check of the service is done through a REST API, so you always know how to manipulate these things. A follow-up from that too was, everything should have a standard API path. Again, it should be obvious, but it wasn't done that way before. For us, as a SaaS company, we deal with lots of customers, and it was important to have a standard way of identifying customers inside our URL. So you can imagine a lot of the servers deal with data that's specific to a customer. Sometimes they deal with data for everything. We wanted it to be consistent. And you'll see later, this actually applies to our network routing layer fairly well. This one is my favorite, most controversial when I have to explain it, but usually people get it over time. Every API is public. As a security company, you can imagine an immediate reaction to this was no way. It turns out this is real important for a lot of reasons, and I'll share the reason why. Before this, we would make an internal service that did something useful, and inevitably a partner, because we have a lot of service provider partners like Rackspace that use our service, would want to talk to it. And we would make a proxy API that was secure and specific to them or maybe a few other customers. If you've got two different systems like that, there is drift between them always. You can't keep up, there's two separate teams, and the team that makes the service really can't be bothered with the public API part of it, so you inevitably have that problem. You also have the problem internally of how do other development teams within your company talk to your service? There's doc, maybe, if they got around to it, right? So you can only really do it when you have time. If you go down the route of this, though, you're pretty much upfront saying we want every service to be documented, tested, reliable, secure, as if it was exposed to the internet, which they are. There's lots of ways to make that secure, but that was the premise. Now, we don't make everything actually available through authorization, but it's all there. We don't make all the documentation available to every end customer, but it's all there for us internally. And a good example of that, we have a service that does billing. And it's purely internal, it processes data and uploads it, and I can control it through an API. We don't document that one, but I have no qualms about it being actually reachable from the internet because we have authorization around it. We also this is actually a screenshot of our webpage. We put the documentation in our console. So every customer can go see it, and actually non-customers too. And when you click into one of those services, you get documentation like this. And if you've seen that format before, it's API doc. It's a Node.js project that does great documentation. It's fantastic for REST APIs. Every single project has this. Another thing that was important as a follow-up from that is we wanted authentication, authorization, and auditing to be built in and pervasive everywhere. No excuses. So we just did that. We made it fast. We solved all the problems about caching and building a framework to make it easy, but it's there. Every single service has this built in for every single API path. There's not a special service that has a backdoor. It's just there, because the service framework won't actually let you specify a method without that. We use kind of a very common way of defining these permissions, just like Amazon does and other places do. It's a colon-separated list, and you can have optional account identifiers, but the general idea is that it's a service and an operation, and you can figure out what things need that permission. The other thing is that every user in our system, every service in our system has its own identity. So if one backend service wants to talk to another service, it can either do it on behalf of an end user or it can do it on behalf of itself. And it's all treated the same. I'll actually show you some Erlang code. This is how permissions are actually done in our code. I've got two examples here. This one is from a service called Ticketmaster. And this is a fairly typical example of I want to create something, and I want to do it only for this account. So if the UI is calling based on my user credential, it will only allow me to create a ticket for that user ID. I can't create it for Mark's, as an example. Compare that to this other service called Auto. As Mark said, naming things are hard, so names are interesting. This one doesn't have account level permissions. This is a global thing, and this is really an internal service for us to manage infrastructure. So anybody that has these permissions is doing it for all users. That's fairly typical of how these things work. Next one was fun, because it actually was a great result. We have no web server. Our UI is done all in JavaScript, and there's absolutely no web application server. It's hosted by a CDN. It talks directly to the backend services securely, and that's it. The cool thing about that is it really helps avoid having business rules in the UI. Obviously, some creep in, but generally not, and the UI team tries not to. But it also means that if the UI can do something, an end user can do it through a script. They can code it, we can code it. Very, very powerful. And, also good for a security company, we eliminate the largest vector of attacks by doing this on our own system. This is where we get into Devops. So 100% of our environment is automated. 100% of the time, there's no shortcuts around that. I didn't mention it before, we deploy fully in AWS. And we're using AWS as CloudFormation to script everything. It was a little bit of work at front, but once we had kind of the framework for doing this there, it just became easy. We've added tools on top of that for continuous deployment, continuous integration, and now it is one of the biggest single positive things I've seen in my career, and I'll get into more details. If you're not familiar with CloudFormation, this snippet right here is an entire service. This is all it takes for someone to create a new microservice. This is, again, Ticketmaster. And there's a little DSL we put on top of this, just generates a little bit more JSON behind the scenes to make it easy for us, but generally this is all it takes. You can kind of see generally what goes on here. We have an AMI. We're actually building a full system image for every service for now. We're changing that to use containers right now, actually, which dependencies it has and which security groups it has. The cool thing about that, if you don't know much about Amazon, is you can precisely control exactly how this service is talked to and by whom, in addition to these authorization things. And every service is like this. And if things are not that simple, like I had a few, we have third-party services that we use. You still have the raw CloudFormation, you can do anything. To give you an idea, I scripted a third-party Windows application on Windows Server to boot up and auto provision its software license from that provider in this format. It wasn't fun, but it was doable. All right, continuous deployment. So I've been doing this 32 years now, and I can say this is the biggest single improvement in my career that I've seen. What we really do is that we release components into production that are small and loosely coupled, just like you would want to do with software modules, but in production. We can do this dozens of times a day, and soon we'll be able to do it thousands of times a day. Amazon does this. It actually makes your life so much easier, and think about what it actually enables. If you've ever worked on a software project that maybe took 6 months or 2 years, and then you ship, the chances of integration bugs is 100%, and you finding them out will take months, right? That just never works that well. And we try and solve that in the industry by making the releases smaller. 6 weeks is good. 6 weeks is still a lot of change. What if you could make one change, submit a pull request in GitHub, and have it online in 20 minutes? We've had interns do that within 2 weeks of joining our company. Now suddenly imagine a migration. Let's say you want to change an API and deprecate an old one. You can do that change queue up all the other clients in the system to change at their leisure, say over a couple of weeks, and then deprecate the old software change. You can do that level of change rapidly. It's not a big project anymore. Yes, you have to worry about things like database upgrades and all that, but it winds up being such a different problem to solve when you have that ability to change things. I also have one of my teams in the UK actually runs that grid computing software project that I talked about earlier. They do releases about once every 6 weeks, and they're high risk. With all the testing in the world, they're high risk because it is a big piece of software, and it's not built using this deployment pipeline. This is actually a screenshot of what it looks like. We use Jenkins to kind of host the tooling and kind of walk through the process briefly. You do a change in GitHub, and what you're actually changing at this point is the version of the service. Your service has actually already been compiled, tested, and built and tagged, version 1.5 or whatever it is. And then we release it as a change to the infrastructure, that JSON CloudFormation I showed you earlier. That goes through, it gets its own integration test. If that works, it actually goes to a staging environment, which is exactly like production, and it has production workflows. If that passes, then we roll it out to production. And for us, that means UK and US-based data centers in Amazon. If any of that fails, they all get rolled back to the previous state without issue. And this works consistently. And let me show you how we actually upgrade a service, because this is actually fun. The box here and the icon, that's an Amazon autoscale group. And if you can guess from the name what they're really designed for is originally was like scaling up fleets of web servers, but they're much more powerful than that. So in this example, we have version 1.0.0 of a service. It's stable. And there's 2 instances of those. There's always at least 2 instances of anything. When we're doing an upgrade, we change the configuration of the autoscale group, and now we have the new instances running and the old at the same time. And depending on the policy of the service, it'll either start taking traffic immediately, or it'll wait till it tests the data, or some other thing. We have new services where we'll actually migrate data processing over in bulks by customer ID because they're a bigger idea. It supports all of that. Effectively, what happens is once a health check passes, they come up and they're stable, we either roll back or we mark this one as good and we move forward. And moving forward, we just ask Amazon to shrink the autoscale group back to its original size. And depending on how you have that configured, Amazon will just turn off the old ones. Or if it failed, it turns off the new ones or leaves them there, whatever you want. Very consistent. Yes, and if there's a failure, we have a manual mode, but basically we do hundreds of these all the time, and it works. Another principle that was super important was the idea is that we shouldn't run our own infrastructure. This one's easy to misunderstand, so let me elaborate a little bit on that. Very specifically, if there's an Amazon service already around, try and use it. Don't go use a third-party database unless you need to. Part of that is it's just expensive. If Amazon's already solved the problem, and even if it's not a 100% fit for your application, you start looking at the actual cost, you'll probably decide the Amazon approach is easier. And as an example of that, we almost exclusively use DynamoDB for our databases now. We do have a proprietary graph database that we use in Amazon, and just to summarize the cost of that, besides the license fees, it's 5 or 6 experts that know the system, that maintain it. It's a lot of code that got built by someone in the room here to actually keep the thing alive and do backups and all that. That's engineering time we could have spent on something else. Now, it was the right choice for us at that time, but it makes you think about it. And if you're left with the choice of, I could run this database and it cost me $1,000 a month from Amazon, or I'm going to spend $2 million on this third-party tool, but it's really easy to code, you might change your mind about what you go and code on. I think developers in general don't think about the operational costs of their software because they're usually divorced from that. This one's real fun. Minimize configuration. This is what enables the adage about treating your cloud instances like cattle, not pets, if you've heard that. Cloud instances are not special. They get special by having configuration on them and state on them. And you should be able to go and delete your servers at any time and have them recreated. You do that by minimizing configuration. And we looked at years of our history before we were in Amazon. Most of the failures we had in production were because someone made a typo to state. One way to fix that is to use something like Chef, right? You can then script all your configuration. Yeah, that works, but you want something even better. You want to minimize that. And the most important thing we did there was use service discovery. When a service comes up, it registers with service discovery, and anyone else can find it dynamically. You just take that problem away, because most of configuration is what database should I talk to, what are the credentials, where's the URL for this service. Just make that dynamic. Let me show you real quick what that kind of looks like from a command line tool. We have normally these are Erlang calls that does this, but we also have little scripts that do the same thing. So in this case, I asked our production environment for the Ticketmaster service. You get back to URLs. That's where it is there, and you can kind of tell they're on different subnets, which is fairly typical. The same thing happens internally, and then the library we have just picks one. It's really that simple, but there's a lot of complexity that goes on behind the scenes, and I'll cover that a little bit later. Another principle that turned out to be awesome. We want to log all the data mutations. We do this in Kinesis, which, if you're not familiar with, is Amazon's implementation of Kafka. It's a persistent distributed log file. And the idea is that anytime we change anything in the system, we just make a record of it. And if no one looks at it, that's fine. But what we use it for primarily is business intelligence and analytics. We do an ETL on that and put it in a database and write reports. But we can also do other things with that. What's interesting about that model is that if you think about what Alert Logic does, is we're collecting that same sort of data from our customers. So we sort of are treating ourselves the same way. Now, we also log those data mutations to a message bus, in this case, RabbitMQ. And there was a lot of debate internally if those should be the same thing or different. Right now, they're different. Mostly because we haven't had a lot of experience with Kinesis at the time, so it made sense to use Rabbit. Dynamic scalability, if you're in the cloud, this one is a must. We did two things here to really enable that. One is if you go back to the URLs I pointed out earlier, is we can actually not only auto-scale a set of instances if they get busy, we can actually use that routing mechanism that we have for customers and pull out customers into their own infrastructure automatically. So if we have a real noisy customer and we want to give them their own private set of servers, we can do that from the architecture level. And we will. We see this quite a bit actually where maybe 10% of the customers are 90% of the volume, if not more. And very pertinent to Jonas's talk this morning in the keynote, we want shared nothing services as much as possible. If you start coding services that way, they are trivial to replace and to scale horizontally. What this really does is by actually putting this in the architecture, it gets the discussion at the developers every single time they write a service. They have to think about it. And actually, they don't have a choice because the first thing that happens with your service is you get two of them, no matter what you do. So you have to think about it right away, and if you mess that up, it'll be really, really obvious. But it takes the choice and puts it front and center because you are, in fact, dealing with a distributed system. You should recognize that. All right, DevOps portion of this. So metrics and monitoring. If you've heard about what Amazon does, they review metrics every day, every week. Pretty randomly about who gets picked. Apparently it's not a good thing to be picked, but the idea is that you're always monitoring your system. We do that as well. And the biggest success for me for this was actually watching the dev teams on their own, the engineers having a meeting once a week and going over metrics and finding problems that weren't obvious. They're actually looking how the thing runs in production. They're not waiting for an outage. They're actually looking ahead and seeing, that looks funny, we should go look at that. To give you an idea, this is one of our dashboards in a tool called Datadog, which is our current favorite monitoring tool. We have dozens of TVs in our office with things like this running. This is probably the least interesting one, but it's the one from my team, so I thought I should show it. This, by the way, is a real-time SQL injection machine learning algorithm dashboard. And the idea is that if that exception box is anything other than green, that's probably a bad thing. But you can kind of tell from looking at those graphs, if any of those graphs start to look out of nominal, there's something going on. And you can see real consistent behavior just by eyeballing these things, even before you would put an alert in like that. And that's just part of what we do now. With that comes an ownership culture. We didn't really have an ownership culture as a company before that, which sounds odd, but it made sense in a kind of a startup mindset where you don't have enough engineers and there's a hot project, and then when you're done with that, you go to the next hot project. We really wanted to change that. And so the main thing is that whenever we create services, they're owned by the team that wrote them for a really long time. And there's some number of services that make sense for a team to own, say a team of 6 people. They'll care for that. They'll continue to improve it because none of the software we wrote has never needed improvements, right? It's constantly changing. And the things that haven't had that, because we have a lot of them from the old days, we actually do business decisions based on the fact we couldn't change the software, which is a terrible thing to do, really. So we wanted to fix that, and it works out really well. Downside of this is, of course, that means developers are responsible for operational production at some level. And that's a really big topic of both concern for the developers and for the business, because we don't want to take too much time away from them. But it winds up being, if you get that balance right, and I think we've got it pretty close, developers will not leave bugs in production for long. Sometimes it's hard. I have one product in particular that's really hard to do this with, but generally you get the right behavior then, which is very rapid system fixes. All right, let me show you how this actually turned out for us, and then we'll cover lessons learned. This is what a canonical service looks like in Amazon. And I'm a very simplified version, but effectively everything looks like this. The boxes are an Amazon availability zone. If you're not familiar with those are effectively physical data centers that are separated by a high-speed link. So, Amazon has a US East region or a region in Ireland, for example. We're in both of those. They have multiple data centers in the city. So we always run at least two, but they're effectively treated transparently the same. Traffic comes in from our API endpoints. It gets routed through a load balancer to an internal routing proxy, who then looks at those URLs and goes, okay, it's this service that we should talk to right now. And that service will talk to service discovery. It'll talk to RabbitMQ, and it will figure out what else it needs to talk to, because usually it's not just one service that's doing a job. And it usually will talk to DynamoDB, and it'll talk to Kinesis. Sometimes there's a SQL database involved. But the cool thing about this is that while our system is not that simple, and in fact, if you threw up our system, it would look very similar to one of Jonas's diagrams from this morning of the spider web. But every service could be understood like this. They are all that simple. And it makes it really easy to train people on what a service should look like and how it should behave, because they're effectively the same. All right, so some of the lessons learned is service discovery is really hard. And if you don't have to do it yourself, don't. One of our best engineers and architects has been still working on this. And he mostly makes the problems go away for us, except when it doesn't, and then it breaks, and then he fixes it. But it's a pretty hard problem. It's distributed state, it really is. And there's some toolkits like Amazon or Netflix Eureka. If you can use that, use that. There's also ways to do it without any of that. Like one classic example on Amazon would be, why not have a load balancer in front of every single service and just use DNS names? That's also an approach. And for our use case, it would actually work fairly well. Amazon itself. So just from like the keynote, every service has to think about high availability and disaster recovery. And that should just be part of every engineer's job. They should understand it. They shouldn't have to reinvent the wheel, but they should understand it. And then make sure they code systems and test systems the right way. This is not something you want to add on later. So you do it from the start, it's actually fairly easy. Fun story there. So if you happen to make a continuous integration and deployment pipeline like we did, make sure you test that too. Because when Amazon's region goes down that's got that, and you only did it in one place, that means you can't deploy to any of the other regions to do your backup plan. So game day testing is important. The other thing that engineers don't like, but I find it fascinating as a software engineer, is the cost management. So you probably have been taught that memory is not free and CPU is not free and bandwidth certainly isn't free, but we don't really get the chance to deal with that. When you're dealing with Amazon, you actually get charged for everything you do. And it's not a lot, but it adds up. So if you start thinking about implementation choices, and one implementation choice might be $1,000 a month, and another choice might be $100, or you could tweak your program to drop that to $2, that's actually fairly fascinating. And what that leads to is actually better implementations. It's really, really cool. The other important side effect of that is that you don't want developers to go crazy. I mean, we constantly have to tell developers to shut down stuff that they're not using. And to give you an idea, our production bill is probably 1/10 the entire bill of our Amazon infrastructure because of stuff like that. Part of that cost cutting is to use containers. Like we did our initial implementation with Amazon Images, AMIs, and it was great. It got us there very fast. Containers are really the way to go now to manage costs, and they're just as trivial to use. They make things faster to build and super easy to deploy in Amazon now that they have ECS. And I wouldn't say they're transparent. We've had a lot of work to do to make them work that way, but I mean, it's going to lower our bill by 50% just by doing that. Right. A good microservice topic is, how big should services be? And the answer is, there's not a good answer, except make them simple, not too simple, right? That's an art form. What we settled on was services should own wholly the data they were responsible for and nothing else. So it's really like one piece of data, one piece of object, something like that, and the service. That has worked out really well. Now what's happened over time, and we knew this going in, there's a microservice pattern called composition of services or composite services where, especially for UIs, you might want to have a service that does a bunch of other back-end operations so the UI doesn't have to know about 10 services, it has to know about one. And we're about the point now where that starts to make sense. Just kind of go into it knowing that that's a normal, healthy thing to do if you're making microservices. Culture. So this is actually my favorite topic of the whole thing, and if anybody wants to talk about this, I'll do this for days. Culture doesn't happen without effort. And a lot of engineers types don't like this topic. And they don't like politics. And let me tell you, they're inescapable. And it's actually not that hard once you just embrace it. I avoided this for so long, even though I've been in architectural leadership roles most of my career. I can only say that if you actually confront this front end, you can actually make huge changes. I mean, we changed our corporate and engineering culture in about a year. And it wasn't easy, let me tell you. I had 6 peers that disagreed with me on every single topic. But in the end, I started changing my expectations, and I changed how I went about convincing them of things. It was more influence instead of, you should do this, right? In the end, I got about 90% of what I wanted out of the architecture. And the things that I didn't get are relatively minor or we've changed to later. It's really powerful to do that. I had to change first before anyone else could change. That's really the lesson there. Politics, one thing I'll add with that, engineers hate it. Here's something to think on. There's politics even with yourself. If you actually embrace that, dealing with other people and getting them to do what you need to do and vice versa is actually relatively easy. But you can't avoid this in engineering. Okay, Erlang. This Erlang conference. What about Erlang? We love it. We've been using it heavily now for over 10 years. It has been a great choice for us. The thing that wasn't a great choice has really been the community support around libraries we need, in particular Amazon support. There's an Erl Cloud library, and I think there's one other one now that has Amazon support. We had to go and add a ton of work to Erl Cloud to get it to work. There's still more needed. And that's kind of been true for a lot of the stuff we do. To give you an example, one of the other projects we're working on right now is high volume machine learning for all that data. And we're not doing it in Erlang because of the lack of library support. And it's the right choice in that case, but if it was there, we would certainly use Erlang. And what we wind up doing is building architectures around the parts that have to be in Erlang because we like it, and parts that just can't be in Erlang because of all this stuff. I've been asked by the rest of my team if anybody wants to contribute to Erl Cloud. We're looking for contributors because there's a lot more work to be done, and we're kind of run out of time on it. Okay, for a quick wrap up. I wanted to show this is actually a picture from a website. We are hiring pretty much nonstop. And we have like 4 locations in the US for engineering and 2 in the United Kingdom, as well as in Colombia. So feel free to talk to me if you want to know more about us. And then that's my contact information, and I got time for questions if anybody has any.
Okay, thank you. Questions? Well, one up the end there. Do you run all this stuff on yourself?
What do you mean?
Do you use your own system to monitor yourself?
Yes.
Okay. So you're the ultimate testers.
Yeah. And sometimes that's annoying because we'll often break our stuff by monitoring it. And I will throw out, too, I am the company's official chaos monkey. I seem to break things more than anyone else just because I go in and touch. I'm not supposed to.
You said you should reuse as much as possible and take existing solutions. Do you see these dependency as a risk now that you're kind of bound to like one system or not?
You mean like specifically Amazon? Yeah, that is a risk. If you think about Amazon today is basically roughly the equivalent of IBM in the 1970s and 80s, right? It's probably a good way to look at them. Certainly there is a risk there. What we did for us, and this was actually orders we had from our CTO at the time, was if we thought about using an Amazon service, how long would it take us to redo it in, say, Azure or Google Cloud if we had to do it from scratch, all hands on deck? And the situation is, imagine we got bought by Microsoft and they wanted us to move to that. And if we could do it within 6 months, reasonably, that was kind of the goal we gave ourselves before we could use that technology. That worked for a while. And then there are things like Kinesis, right, which really doesn't have an equivalent in Azure unless you kind of did your own Kafka deployment, so we kind of satisfied ourselves for that. I think the reality is the cloud platforms have diverged a lot now. And Amazon, I mean, if you go to reInvent or watch what they come out with, it's remarkable how much they're producing and you can use. So it is a risk, and there will be issues with that. I think we're pretty comfortable with it knowing how long it would really take if something dramatic happened. We could re-implement the system. Certainly from a design perspective, there's nothing in there that's specific to Amazon. Even some of the newer stuff we're using would be like Lambda functions. There's not an equivalent to that anywhere else, but you could do your own without too much trouble. So, yeah, but certainly the business asked us that question to make sure we just didn't decide to use, Candy for fun.
Okay, some more questions.
Thank you. That was a nice talk. You mentioned Earl Cloud,
Yep.
and that there's still some work. Could you maybe elaborate a bit on what is still missing and how much is supported?
I think the one example I just heard is that we got a request from the community for something with ECS, which is Amazon's Docker service. I don't think there's any support for that. There's probably a lot of that. We typically, in Alert Logic, we have a dozen or so services that we use, and we don't care about the rest. We're not actively maintaining it as a general purpose API. And it wasn't written by us originally, we just sort of have been adding a lot to it. So it's mostly somebody that needs to go on and take it and kind of love it, make it equivalent to the Amazon APIs, because they change constantly. And if the community is waiting for us to do that, I mean, it's going to be hit and miss on how fast we'll get to it. But I know ECS is one of those.
Okay, so if you are making changes to it, then it'll be things that are specific to what interests you rather than the general sense.
Yeah, unless somebody wants to take over maintenance of it,
well,
which always sounds fun. It sounds fun to me, actually, but, in my spare time.
So we are currently in a similar situation with regards to migration to containers.
Mm-hmm.
And we've been migrating our services to actually Kubernetes cluster that we are hosting on AWS. And from what I've seen with your diagram with the service discovery and load balancers and all that stuff with services and keeping a track of deployments and so on and so forth, it seems like you're describing Kubernetes pretty much.
Yeah.
Have you considered it yourself, using it yourself?
We did a little bit, and honestly, I don't think we ever did an exhaustive evaluation of it. Probably, honestly, of most things in this system. We tended to have some preconceived notions about what we should use. And certainly for us, there was a tendency to want to use Docker-based solutions, so when Amazon came out with ECS, it was just there. Same thing with Netflix's Eureka. I could never get the guy looking at services at Discovery to ever look at it. And that's okay, like it didn't actually impact us, but yeah, that's a great example. And I think if you had come in today with a different set of people, that would have been an obvious choice to make. I just don't know if it would have really mattered, like how, it's a choice of how you do it. Does it save you anything? Maybe, maybe not. Yeah, it's really interesting. The one thing I'll add to that that's just interesting that you might be interested in, the only thing we really had to worry about with ECS compared to running machine images was the network identity doesn't exist. So port management and all that had to be transformed a little bit. So there was a little bit of coding to do as well, and then that was pretty much it.
Okay, just an advice. If you haven't looked at Kubernetes over the past half a year or a year, check it out.
Yeah.
They've moving forward so fast. They're adding features constantly, and I think, like from what I've heard here, I think it might be a really good fit for your company.
Yeah, and I think a lot of places that if you're doing this sort of thing from scratch, unless you know your scale is insane, which now the scale of what qualifies as insane is really high, yeah, use something like that. I mean, we could build a lot of our system that way very quickly. What's interesting about us, and I think a lot of places, is that those toolkits may not have been where we needed them to be when we started, and so then they'll get discarded. And then you go down a path and it's hard to change, yeah. Yeah, but thank you.
Thank you.
Mm-hmm.
Time for one more here.
Thanks. Thanks for a great talk. I have a question about culture, which you had a sort of a red thread throughout the presentation. Culture is always a little bit hard to assess. It's more like the holistic part of development. But obviously, coming from a company that does microservices itself, and a lot of interesting things, there's a lot of things to recognize here. And I was wondering if you could sort of like give some concrete examples of how culture has had a profound change or effect, in both directions, actually.
Yeah,
in
sure.
this transition.
Yeah, probably the biggest thing that changed for us, like externally, like if you were outside in the business looking at engineering, is now engineering talks to one another. You know, we're actually trying to make software for the rest of engineering to use more than anyone. We treat them as users. Before that, it wasn't the case. And that meant all the little things like doing good doc or talking to your clients didn't happen. And I wouldn't say it's perfect. Like, this is a hard problem to get going. But what I really wanted to, and I actually talked to Mark Allen about this quite a bit, was we wanted to start to treat our internal code like open source. Like, what makes a successful open source project? Good doc, listening to your customers, making rapid changes. Why not do that internally? So we started asking the engineers, especially those early engineers who were really the smart, productive ones, you know, the ones that were crazy coders, the 10Xers. You guys don't need that, but how would you make everyone else want to use your code? And that was usually the answer. So we got people thinking about that, and that had all these little behavioral changes, besides docs and testing. Little things like we had READMEs in our GitHub projects for our internal code modules that were actually useful, that tell you how to check out the project and use it, you know, which before didn't exist. Before, when we wrote doc, it was just Erlang doc for the APIs. That's probably the best example. And I think everything else is a fallout from that kind of behavior of being responsive to your customers, the internal customers.
Thanks.
Mm-hmm.
Okay, any more questions? Then we are done.
Great, thank you all very much.